Welcome to another strategy session. I'm absolutely thrilled to have you here today. If you're a focused learner, especially one gearing up for those challenging Cambridge 0606 additional mathematics papers, and you're looking to seriously level up your understanding, well, you're in exactly the right place. Today, we're embarking on what I like to call a mathematical ascension. We are completely decoding trigonometry. Look, I know it's easy to see trig as just another tedious chapter in a massive math textbook, right? Just a bunch of buttons on your calculator. But it is so much more than that. Trigonometry is, quite literally, the hidden code of the universe. It's the mathematics of waves, of circles, of cycles, and even massive architecture. By the end of this explainer, you're going to see exactly how moving from basic triangles all the way up to infinite waves gives us the ultimate vocabulary to describe reality itself, and, of course, to absolutely ace those exam questions. Take a look at this magnificent structure. This is the Chichen Itza Pyramid. It's an absolutely breathtaking piece of ancient architecture. But for our purposes today, it's a massive real-world geometric puzzle. Think about it. How do we actually estimate the angle that the sloping sides of this pyramid make with the horizontal ground? I mean, we can't exactly slice it in half with a giant 100-foot protractor, right? We need a system. The great astronomer Galileo once said that the laws of nature are written in the language of mathematics, and its symbols are triangles, circles, and geometric figures. Without those tools, it's impossible to comprehend a single word of the universe's design. Today, we are going to master those exact symbols.
All right, Section 1, the foundation of triangles. Let's start with the absolute basics. Okay, let's dive right into this. You probably already know the legendary acronym SOHCAHTOA, but let's really think about what it means. If you have a right-angled triangle and an angle, let's call it theta, that sits nicely between 0 and 90 degrees, these three basic ratios unlock the entire shape. Sine is simply the opposite side divided by the hypotenuse. Cosine is the adjacent side over the hypotenuse, and tangent is opposite over adjacent. Now here's the crucial thing examiners want you to understand. These aren't just arbitrary rules we made up. They are fixed, absolute proportions. They remain completely and totally consistent no matter how astronomically large or microscopic the triangle gets. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get back to the math.
Now, as you move into higher-level papers, certain angles occur so frequently in mathematics and engineering that we just have to rely on their exact values, specifically 30, 45, and 60 degrees. Top students completely memorize these specific surd and fraction values. It's a total game changer. For instance, knowing instantly that the sine of 30 degrees is exactly 1/2, or that the sine of 60 degrees is the square root of 3/2, or that the tangent of 45 degrees is perfectly exactly 1. Memorizing these values allows you to seamlessly process complex calculations, especially on non-calculator papers, without breaking a sweat. It keeps you right in the flow of problem solving.
But here is where we hit a fascinating conceptual wall. Think about it. Our classic right-angled triangle has a hard maximum limit. The angle theta has to be between 0 and 90 degrees, right? Because the right angle takes up the other 90. So I have a fundamental problem to pose to you. What happens when angles exceed 90 degrees? How in the world do we calculate the sine of 120 degrees or the tangent of 300 degrees when a right-angled triangle literally cannot hold an angle that large?
That brings us to Section 2, angles beyond 90 degrees. This is where the magic really starts. To answer that question of angles over 90, we have to graduate from the simple triangle and move into the broader 360-degree coordinate plane. By placing our angle right at the origin of an xy axis, inside what we call a unit circle, we can allow our angle to grow to any size. It can rotate forever, infinitely. But as we move into different quadrants of that graph, the x and y coordinates become negative, which mathematically changes the signs of our trigonometric functions. There is a brilliant, essential shortcut to remember this for your exams: the cast rule. Starting from the bottom right, the fourth quadrant, and moving anti-clockwise, we spell CAST. In the first quadrant, all functions are positive. In the second, only sine is positive. In the third, only tangent. And in the fourth, only cosine. It's an elegant, instantaneous map of positive and negative values, and you absolutely need it in your mental toolkit. Now, what's really interesting here is that our trigonometric toolkit actually has 6 tools, not just 3. We have our primary functions, sine, cosine, and tangent, but we also have their reciprocals.
By simply flipping the primary fractions upside down, we derive cosecant, secant, and cotangent. So cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. A quick pro tip, don't let the names trick you. Cosecant goes with sine, and secant goes with cosine. It's kind of the opposite of what you'd expect. They follow the exact same positive and negative quadrant rules as their primary partners, but they open up entirely new algebraic possibilities for those tricky proof questions. Moving on to Section 3, Graphing the Infinite Waves. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get back to those infinite waves. We've explored the triangle. We've completely conquered the circle. Now let's look at the majestic sine and cosine graphs to see what actually happens when we plot these values continuously over time. Imagine taking that unit circle we just talked about and unrolling it onto a flat piece of paper. You get a continuous, perfectly rhythmic wave. Both sine and cosine have an amplitude of 1 unit, meaning their absolute peak is at 1 and their lowest trough is at -1. They are periodic, perfectly repeating themselves every 360 degrees, or 2 pi radians if we're working in radians. But here is the most beautiful, mind-bending part. The cosine graph is exactly the same shape as the sine graph, just translated 90 degrees to the left. They're essentially the exact same wave, just shifted slightly in time. The tangent graph, however, well, it's a completely different beast. While sine and cosine are these smooth, continuous, predictable waves, the tangent graph violently breaks apart. Why? Because mathematically, tangent is sine divided by cosine, so whenever cosine equals 0, which happens at 90 degrees and 270 degrees, we are literally dividing by 0. As the angle approaches 90 degrees, the tangent shoots upward, rapidly approaching infinity. At exactly 90 degrees, it is completely undefinable, which creates sudden, invisible vertical walls on our graph called vertical asymptotes. You'll need to clearly mark these with dotted lines in your exams. Section 4. Transforming trigonometric graphs. This is where we separate the top-tier students from the rest. Understanding those base graphs is fantastic, but the real world and real exam papers don't always fit into a perfect basic sine wave. Sound waves can be loud or quiet, high-pitched or low-pitched. Here is the ultimate blueprint for transforming any trigonometric graph, using the equation y equals a sine bx plus c. The a changes the amplitude, making the wave taller or shorter. The b changes the period, compressing the wave or stretching it out horizontally. And the c shifts the whole thing up or down on the y-axis. So the absolute crucial point is this. When sketching these transformations, you must follow this exact order. First, apply the vertical stretch from a. Then, the horizontal stretch from b, remembering the scale factor is actually 1 over b. Finally, apply the vertical translation from c. If you try to translate before you stretch, you will warp the data, the whole shape falls apart, and you lose those precious marks. Finally, Section 5, Proving Trigonometric Identities, the final boss of trig. We are now ascending to the final stage of trigonometric mastery. We're moving beyond just solving for a single missing angle and stepping into the realm of absolute universal mathematical truth. Let's clearly define an identity. An equation is only true for certain specific values. It's like finding a single specific key for a specific lock. But an identity is a mathematical relationship that is true for all values of the variable. It's a master key. The most famous one, derived straight from Pythagoras' theorem applied to our unit circle, is this. Sine squared theta plus cosine squared theta is identically equal to 1. Note the 3 lines for identically equal. This incredible fact remains true whether theta is 5 degrees, 500 degrees, or -5 million degrees. In advanced exams, like your additional math papers, you weren't just asked to solve, you are asked to prove. You have to prove that a massive, messy, complicated string of functions is actually identically equal to something incredibly simple. Here are your tactical proof strategies. Method 1. You manipulate both the left-hand side and the right-hand side until subtracting one from the other equals precisely 0. Method 2, which is honestly the strategy most top students prefer, you deliberately take the ugliest, most complicated side and you use your known substitutions, like replacing tan with sine over cosine, or swapping out 1 minus cosine squared for sine squared, until it elegantly collapses to perfectly match the simpler side. There is no better feeling than getting to that final line of working. And this brilliantly illustrates exactly what we discussed at the very beginning of our session. Galileo told us that the universe is written in this very language, and you have just ascended through the vocabulary. From the simple ratios of a right-angled triangle, to the coordinate geometry of the cast rule, to the infinite periodic waves of sine and cosine, and finally to the undeniable universal truths of trigonometric identities. You aren't just memorizing formulas here, you are quite literally learning how to read the blueprint of nature itself. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. So I have a final question for you before we wrap up. Look around you right now. Seriously, look around. The light hitting your eyes, the alternating electrical current powering the screen you're watching this on, the structural angles holding up the very building you're sitting in. What invisible waves, cycles, and angles are just waiting for you to measure and understand? You now possess the tools to do it. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep learning, keep practicing, and go decode the universe.